Okay, good morning, people. Uh, Unfortunately, yesterday I did not switch on the recording camera and so missed out on that. So, what I plan to do is I would be revising what we had done yesterday very fast and or possibly doing only that. So, we may and conclude the lecture early, but then, as I said, that I had asked you all to draw the diagrams. I have just received a few of these diagrams. I would want to show them to you all, and I would start with this one. Okay, Tushar has come up with very good diagrams. Okay, this is absolute instability. Okay, beautiful diagrams, and I think this is the next one. Yes, this is conditional instability. Okay, it's not only drawing it well. You'll see that once you draw it so well, you are so very well known to what exactly is happening with that. See the tendency going up, going down in absolute stability. Actually, we start with this diagram, and this is the common graph that he has drawn. Okay, so you'll see that conditional instability is a very interesting condition. And as I said, when if you are going to place the scale in a peculiar way, you'll see that in the text in the photograph that I showed you. Okay, these two lines here were so very near to each other. These lines, sorry, I'll be using these two lines are so very near that we are. But here in his diagram, we can we can observe there is a slight change. It goes down and then of course it crosses up to come up with what is called as conditional instability. Okay, now besides that, I have received one more. I think it was Shreya. She has drawn these diagrams. Okay, here again, you'll see that in this conditional instability, the positions are changing in individual students. But here again, you'll see that it dips below the environmental lapse rate and then it crosses up. Okay, so this is also a good representation, I would rather say. And the third one I see is from Pritham. Let me see. Yeah, this is this that Pritham has shared. Okay. He again has put up absolute stability to start with, and then you have absolute instability. He has tried to replicate the photograph that we had, and then this is conditional. This is what conditional instability. Yeah. Okay. But as I said, that if you are using the same scale that these textbook walas were using, or the Luton and Turbo book walas were using, one could get confused as far as the lower aspect of the curve is concerned. Okay, and in that case, you'll see that the other two are more clear. Okay, one by Shreya and the other one by Tushar. As such. So this is one thing that I wanted to just reflect on. Stop presenting here. And let's come back to what we were doing yesterday. Of course, this is a continuation of that. In fact, let me tell you that these diagrams that I have shown you on a very micro scale, it also is an air mass. It is an air mass. What exactly is an air mass? We can understand an air mass. I'll just put it up for display. This is what we had started with yesterday, right? That an air mass is a large body of air, okay, and the temperature, the moisture content, the lapse rate, okay, is uniform horizontally. Now, initially it was believed that it is uniform horizontally, but later you'll see that it was confirmed that not only horizontally but vertically also that particular packet of air is going to have very similar conditions of temperature. Now, one would say that, sir, how is this possible that if I'm going to climb up in that particular air mass, the temperature obviously is going to be different. So nobody's challenging that fact that the temperature is going to fall. but you'll see that if this is the packet, okay, at this end and at this end, the lapse rate is going to be the same, okay, and that gives the uniqueness to that particular air mass. Otherwise, okay, and yesterday we spoke about the fact that all these red ones, right, all these red air masses, okay, these are the warmer ones, and those beyond this, okay, these are going to be the colder air masses. This is the primary distribution you could have as far as classification of air masses are concerned. And as far as the secondary classification is concerned, okay, this is of course the geographic one, and within the geographic one, uh, you would say that the source regions. We spoke about the fact that this is the land is going to be the source region as such. And incidentally, you'll see that why is this, or rather, why can this be called as an air mass? You'll see that the conditions are semi-arid, right, from this part of Sahara all the way into the Arabian desert, all the way into this part as well, and all the way into Tibet. Okay, so all of this is going to be drier conditions. Okay, and that's why. Okay, yesterday we spoke about this also as the continental, tropical, as the location. As once we speak about the the latitudinal extent, the geographical extent, we come down a bit as far as the scale is concerned, and we see the source based on the surface below. If it is land, we said it's going to be called as continental. The sea represents that continental aspect, and sorry, yeah, the continental aspect, and the M represents the water part of it, maritime. Okay, so this was the basic classification. This was also called as the geographic classification of air masses. As you move towards the equator, they get warmer, and as you move away from the equator, they are going to get cooler. Is the geographic classification. Then we came to the thermal classification. The thermal classification is the fact that whether we are going to call a particular air mass warm or cold. Now, how do we call a particular air mass warm or cold? Let us say this is the surface, and of course, this part is the temperature of a particular. Um, this part is the air part of it as such, and you have a air mass which from some other area it is going to move into this. And what I told you yesterday was significant, was right. I had just had to confirm it because of I had a confusion that now you have one air mass, the local air mass, and then you have the traveling air mass, which is this air mass. Now, if the temperature of this air mass is going to be higher than this, the temperature of this air mass is going to be higher than this is going to be called as a warm, higher, so it's going to be called as a warm air mass. On the other hand, you'll see that if the temperature of this air mass is going to be cooler than this is going to be called as the cold air mass. I told you all yesterday that in symbolic representation, cold air mass is referred to as K and not C, as cold is spelled in English. It's referred is with reference to K. Another thing, now if this is supposed to be warm, then how would the associations be? Obviously, this would probably be a tropical air mass, and the winds from the colder air, or air mass from the colder parts, is going to come and settle down. So this is going to be warm, this is going to be cold, so this is going to be colder air mass. If this is going to be, on the other hand, if this is going to be the colder regions, higher latitudes, and this is going to be moving from the tropical regions into these regions, then this is going to be warmer. Let me tell you that this is for the explanation purpose. You'll see that within cold area, within warm areas, also you could have mixing of air masses, and in fact you have that at a larger scale and more regular scale. This, what I'm speaking about, the colder regions and warmer regions, happens seasonally, but you'll see that very regularly you have local air masses which are going to show. These two could be, both of them could be cold air masses. This could be cold, this could be cold as well, but then when it comes down, the temperature of this, it could be colder than this, and that's why you could call this as cold. And on other scale, this could be warmer comparatively to this, so you could be calling this as warm. As I said, temperature is a very relative concept. Same way in the tropical regions also, you could have two tropical air masses which come together, and you could have a condition wherein you would have both of them are warm originally from the source as such, but within that it may so happen that this could be warmer than this, thus you may be calling this as the warm within the tropical, and you could call them on the other hand, this could be cooler than this, and as a consequence you could be calling this as a cold air mass within the tropic. So all these combinations you always have to keep in mind, because all of this is a very dynamic process. Having said this, okay, when we speak about development of an air mass, how does an air mass develop? We've said that it's just a large body of air, it's a large mass of air over a particular region. Now, how does this region need to be? What is the source region? There are some basic requirements as far as a particular air mass picking up its characteristics are concerned. It should have an homogeneous surface. Homogeneous in the sense it should have land, all of it, or it should have water, all of it, on a larger scale. If you come to a more localized or a more regional context, then you could see that within land it should be mountainous, it should be plateau, or it should be plain. Okay, so you could have differences accordingly. You see that plains would heat up faster, and mountains would not heat up that fast. So there again could be differences in these. Okay, air masses would normally develop where there is divergence. That means where there are high pressure areas. It's not a thumb rule though, but then that is how it happens, because as far as converging areas are concerned, okay, they would not settle down. Okay, because let me tell you that for an air mass to come up to a particular characteristic, it has to settle down for a significant period. Now, if the weather conditions are not allowing the air mass to settle down, how will it pick up the characteristics? Okay, the continental characteristics, the warm characteristics, the unstable characteristic. It will not be able to pick up unless and until it gets stable for a considerable period of time. And that's why you'll see that convergences are normally say avoided, because the moment you're going to have convergences, you're going to have gradients. Because of that, you could have difference in temperatures. So obviously there is going to be climbing and there is going to be subsiding. So there's going to be a mixture and all. So these such conditions are obviously not going to be favorable. On the other hand, high pressure divergence areas are going to be stable for a significant period. As a consequence, such conditions are favorable as far as development of air masses are concerned. Atmospheric conditions are going to be need to be stable. Now, actually, this is an say a continuation of the second point. When I say convergence and divergence, I'm saying it from a different sense, physical sense, or the sense in physics as such. But what I mean by atmospheric conditions is nothing but the same. Okay, you'll see that atmospheric conditions tend to be unstable when there is convergence. I've just said atmospheric conditions would be stable when there is divergence. So this is a fallout of the second point, but then requires a separate mention, because that the second point is more process based, the third point is more geography based, I would say. As far as source regions are concerned, it may so happen that a particular mass may not have that much of time to settle down in a particular area, or in some cases, because of divergence as such, a particular air mass stays there for a significant period of time. On those bases, the characteristics that these air masses pick up from the local conditions are going to be unique. And on those bases, they will be also be called separately. In the sense, if an air mass is going to be there for a significantly long period, it gets very solid characteristics of that particular air. And that's why thus such an air mass, such a region, in fact, is called as a primary source region. But if the air mass is moving and it has not been stable for a significant period of time, stays there, starts acquiring, has acquired some of the characteristics, but then weather conditions change and the air mass has to move, then this is going to be called as a secondary source region. And that's the basis on which we identify the sources and the characteristics of air masses. As far as study of air masses is concerned, you'll see that this in fact is related to something that we are going to do tomorrow. That's related to the fact that the frontal theory, or what was called as tropical cyclones. Okay, you had this person named by the name Jerkins. Okay, and those who attended offline classes for a couple of days that we conducted in the rooms, I did refer to this anomaly. Okay, that Jerkins is spelled this way. Okay, he was a Swedish climatologist, and he was studying on what are called as temperate cyclones. He was studying what are called as temperate cyclones. In that process, he came up with what is called as the frontal theory. Okay, and in all that studies, he said that all this happens because of air masses. Now, it was obvious that if these air masses are happening in the temperate regions, okay, you'll see that Sweden is somewhere here. So Jerkins belonged to this, so it's exactly under these air masses. So he was studying, and this again, 60 degrees is where you're going to have these temperate cyclones. Temperate cyclones obviously are not as harmful as tropical cyclones. So they were studying all these things, and they said that if these are conditions in temperate regions, you could have conditions in the tropical regions also. As a consequence, they started studying all these, and eventually this whole classification of varied sources and varied characteristics of air masses came up, and eventually we had so many classifications. What are these classifications? We have spoken about these classifications. We spoke about the geographical classification. We divide them into those coming from the tropical areas and those coming from the polar areas. Okay. Then you'll see that those coming from tropical and polar areas individually are further divided into those coming from say ocean surfaces, and those coming from continental surfaces. Similarly here also continental and sea surfaces. Okay, so this is more to do with the geography of them, and that's why this is called as a geographical classification. Then comes the thermodynamic classification, wherein I've just said that whether a particular air mass is cold or warm, that decides the characteristic. Okay, and then you have, okay, when the cold and warm come together, obviously there is going to be some mechanics that is involved. It would either go stable or it would either go unstable. So a mechanical classification divides it into two, that's stable and unstable. And eventually it was found out that though these were initially classified separately, they all of them could be put together, and that was called as a composite. That was called as a composite classification. And a section of the composite classification can be seen here. I picked this up from the net. I'm planning to make up, surprisingly on the internet, we don't have a very good explanation of it in a diagrammatic format. I don't know whether I was searching it wrong, or whether they actually is not, because this again you'll see that it seems so much stretched. So I plan to come up with a slide wherein I would be giving you a detailed composite classification of air masses. But then one of this, you'll see that you have how many? 1, 2, 3, 4, 5, 6, 7, and 8. Okay, all of this is with regards polar. Okay, so 8 of polar and 8 of tropical. Okay, the basis is going to be similar. You are going to have 16 types. We spoke about this yesterday also, that we have around 16 types of air masses, or in all. How do we divide them? Kaal fakta apan, we divided them in this way. Today, what we have done is we just shifted it. Okay, every polar air mass is going to be further geographically divided into, okay, continent. The polar air mass coming from the continent. This is one here, or rather, this is A, and this is the maritime coming from a sea area in the polar areas as such. So this is going to be B. Okay. And then you'll see that each of these are further going to be uh, identified at whether the polar continental is warm or whether the polar continental is cold. Okay, this is how you read through it. Okay, now this one here, whether the maritime polar is cold or whether the maritime polar is warm. When they come together, obviously we will see whether it is stable or unstable. So whether the continental polar cold air mass is stable, okay, this in fact should have been, these are the mistakes. here, okay, because you'll see this is unstable, so this should be U and not an S. So this is going to be continental polar cold unstable air mass. Now this is continental polar warm stable, continental polar warm unstable. I'll change this tomorrow. Remember, this is wrong. Okay. So if you go logically, another reason to identify this is if you go logically, you will not create a mistake. Okay. Then this is maritime polar cold stable. Maritime polar cold stable. Maritime polar cold. This again has to be U. This is unstable. So this is again wrong. So these two changes have to be brought about. And the last ones of them is maritime polar warm stable. Sorry, maritime polar warm stable and maritime polar warm unstable. Okay. Instead of this, what you can do is you can write a T here. The rest of the classification remains the same. ओके. फक्त एक काम करायचं, इकडनं पी काढायचा, इकडनं टी लिहायचा, इकडनं पी काढायचं इथे टी लिहायचा, इकडनं पी काढायचं इथे टी लिहायचा, ऑल द वे डाउन. All you have to do is just remove the T, and from here, okay, from polar, instead of polar, you say, sorry, tropical, tropical. Cancel this, cancel this, cancel this, cancel this, cancel this, cancel this. Instead of that, use the word tropical, and you get the possible combinations of tropical air masses. What you have in front of you is the possible combinations of polar air masses. Just remove the P and put in the T, and instead of polar, write tropical. You'll see that you get those 16 air masses that are that are reflected out of the tropical air masses as such. Okay, this is what we were referring to yesterday. Uh, this is something that we have done yesterday. As I said that uh, the source of the air masses remains the same. As I said, because of the shape and the size of the North American continent, it becomes very easy to uh, place all the air masses around it. So invariably, you'll have pictures like this instead of having pictures of the Asian continent. The Asian continent is very large in land size, and that's why putting all of these around it becomes very difficult at times. But then you'll see that here these are what? These are winter conditions. So obviously the continental Arctic is going to be very cold and very dry, and you'll see that the expanse of it is going to be huge, and of course it is going to move southwards from here. Okay, this comes from the continental parts of Greenland and the northern parts of Canada, etc. And similarly, you're going to have the maritime polar, which come from the seas around the Aleutian Islands, and here the North Atlantic Ocean. Okay, so they could move either ways. And as tropically, you'll see that in the winters, okay, you won't have, because this is cold. Okay, the land surface is cold during the winters. You don't have a tropical continental air mass, which will be coming up in just a few moments. Then you are going to have maritime, tropical maritime. You'll see that the Pacific Oceans is the air mass above the Pacific Oceans here is going to pick up, and it's going to move in this direction. And here the Atlantic and the Caribbean Sea is going to again build up what can be called as the maritime tropical warm humid. Okay, you'll see that this invariably, we spoke about this yesterday also. Air masses coming from water are going to be humid, and air masses coming from land obviously are going to be uh, not humid, or they're going to be dry. Okay, here you'll see that there is a change because now we have moved from summer to winter, and not only have these moved up a bit. Okay, you'll see that the polar air masses have moved up, this has receded. Okay, and you'll see that the area occupied by the continental polar is less, and to compensate that, you'll see that this one has increased significantly, and the space here again has come up with what is called as the continental tropical hot and dry. Okay, continental means dry, tropical means hot. Okay, and here you're going to have those humid ones which are going to bring in rainfall, okay, in these regions. Okay, so a very easy way to explain these various combinations of uh, air parcels or air masses you may find on the surfaces of different parts of the world. Here you will see it in on the North American continent. Okay, as I said, the study of all this started with uh, say the basic study which was initiated by Jerkins, and when we meet tomorrow, we are going to do the theory of the frontal theory of Jerkins. Again, an interesting theory, a significant. The mechanisms of what Jerkins had to say has been done by us at an earlier point in various locations. What we have to do is we have to identify the context of Jerkins' theory tomorrow, and we will then go into the details of that. Okay, and while doing that, we will see the process of how this happens. Okay, in addition to what all we have done today, what we are going to add to it tomorrow is the process and how this actually process gets dynamic. Okay, we are going to see different types of fronts. In fact, yeah, here, okay, you'll see that I have had different types of fronts. This is a warm front, this is a cold front, and occluded front. We are going to see what this is, and we're going to see a stationary front also. uh, let me tell you that these are various stages in what is called as a temperate cyclone. And tomorrow, whilst we meet, we will be seeing the details of what this is going to be. Now you'll see that this complete process happens in the temperate region. In spite of that, you're going to have a warm front and cold front. So that is that is something that we have to understand logically, that temperature is a relative concept. Okay, you could have warm and front within a polar a temperate region, and you could have warm and front, a warm and cold front, sorry, within a tropical region also. More to follow about this, the Jerkins theory and the frontogenesis that he speaks about. Okay, how they come in front of each other, and then how you'll see that the cold comes from one side and the warm comes from other side, and you'll see that because the cold is heavier, it's going to go down, and this is going to help the warm to pick up. What happens at this particular location is what he has explained as frontogenesis, and this is very interesting to understand, and how these things happen. Now, having understood frontogenesis, precipitation, understanding precipitation even in lower latitudes gets easier. Okay, so all that to be done tomorrow. We'll stop here today, and let me stop sharing, and I will end my show here. Discard these things, and yeah, coming back to how long has this been? I don't think this has been more than half an hour, I said, but as we had done most of it yesterday, this was just a revision, and as a matter of fact, we needed a record of this so that you can come back and view it at any point of time you want a reference to it. I'm purposely not going into frontogenesis because I want you all to again revisit what are air masses, and in fact, if possible, okay, yeah, I think um, Preetham has posted us a copy of this. You could go into the topic on air masses and understand the characteristics. Of course, uh, as I said, that having understood the basic characteristics of air masses, writing about each of the air mass is easy. But then, just to go into the theoretical aspect, you can just go through them. You have them in the book by Turbuck and Lutens and Turbuck also. So any of this, just visit the chapter on air masses and just see the characteristics of these respective air masses. They have given regional characteristics. We spoke about general characteristics. You'll see that, say for example, I did say about the fact that why don't we take a diagram of the Asian continent? You'll see that the continental polar air mass on Asia is going to be much larger as compared to the continental polar air mass on America. So obviously the characteristics are going to be different. Broadly, we are going to call them the same, but the characteristics are going to be different. You'll see that the one thing I would say that the lowest temperatures of on Siberia are going to be much low as compared to the lowest temperatures on in somewhere in Canada. As such, the lowest point in Siberia and the lowest point on North American continent is going to be different, basically because of the characteristic, the sizes of it. Then speaking about the maritime, okay, you'll see that the maritime air masses on the Pacific Ocean, given the size of the water body, is obviously going to be larger as compared to the say the maritime air masses which would develop on the Atlantic Ocean. Comparatively, you'll see that the Pacific is much larger than the Atlantic Ocean, isn't it? So that is it. And then while they move into, okay, you'll see that the shape of a particular continent is also going to make a serious impact on what the impact or what a serious impact on the process as to how moving air mass is going to act and behave when it goes into a particular region. Then you could have, you'll see that as compared to Asia along the Americas, okay, particularly North America, you have this boundary of the Rockies, okay, that is going to hold on these the movement as such. So all these minor things will come into context, and that is why I would suggest that you should be रीडिंग थ्रू जस्ट जनरल रीडिंग की तुम्ही तुम्हाला कोणी डिटेल मध्ये काही विचारणार नाही बट जस्ट जनरल रीडिंग to get a grip on how the conditions and the characteristics of all these air masses change with regards the source region, the size of the source region, when they move into a particular region, the temperatures of the local air mass, and so on and so forth. So these are such many wonderful combinations that could interest one at an individual at any point of time. So that is all from me for the day. If you have any questions, you could ask me those questions.